Hi, welcome. I'm going to give it a minute or so before I get started. So hang tight. All right. Hi, welcome to this Tecton webinar, Supercharging Production AI with Features as Code. My name is Sergio Ferragut. I'm a developer advocate here at Tecton. A little bit about me. I've had too many years in the data space, over 30 years in the data space. I've played many different roles. I've been a software engineer. I'm building transactional systems, interacting with transactional databases. I've gone into the analytics space and built data warehouses, built ETL pipelines. I've done pre-sales, post-sales in that. I've done some software architecture. I've been a data engineer, built streaming pipelines for IoT use cases and anomaly detection. And more recently, I joined Tecton a few months ago, and I've been learning about how easy it is to create feature pipelines, so machine learning feature pipelines with Tecton. And I'd like to share what I've learned so far with you today. So today, we are going to talk about the data challenges in AI, what the problems are, and we'll go into the Tecton architecture and how it helps solve many of those problems. We'll talk about the developer experience, so what it looks like for you to use Tecton as a data scientist, as a data engineer. And I'll do a little demo of the platform and build a streaming pipeline with you. So any machine learning presentation has have the obligatory Andrew quote. So this one's a pretty famous one, and the basic idea here is feature engineering is important for machine learning and for delivering machine learning functionality to applications. But feature engineering is hard, right? The feature engineering time is usually long. It takes, it's not just the data science and building and training models, but it's delivering those pipelines into production so that the features can be recreated on time to deliver and to serve online model for prediction or for classification or even for generative AI. There are problems in training and serving skew, right? Getting the training data set that has the point in time correct values for the features that as they're going to be seen at serving time is a problem to solve, and it can get complicated. There's infrastructure management, right? There's a lot of infrastructure to manage in order to build the training data sets, in order to deliver the serving pipelines and the serving infrastructure to deliver the throughput and the low latency that's needed to deliver this functionality. And all of that creates a lot of compute inefficiency. So you have to worry about compute efficiency, right? And optimize your workloads, reduce the workloads where you can. And also because this is data and this is events and people's data, there's a need for governance. There's a need to audit changes. There's a need for monitoring the pipelines and monitoring access, and even having the ability to reuse other people's work, other features from other teams. Why is it complex? There's a lot of things to deal with, right? Data engineers, data scientists, and MLOps engineers have to deal with all sorts of infrastructure, from streaming data sources, batch data sources, unstructured data, real-time data. They need to build stream processors to process the streams, batch processors. They need to create forward fill and backfill operations to feed the offline and online stores. They need to manage the feature serving infrastructure and deal with generating training data with all sorts of different orchestration tools like Airflow, Spark, Snowflake, Beam, tons of different tools. And this is just a sampling of the tools that can be used in these pipelines. So the data scientist, the whole ML team, the data scientist, the data engineer, the ML ops engineer need to do a bunch of tasks that are sometimes duplicative, right? The data scientist needs to create, to process raw data from wherever they can get the data, and create some complex transformations, build point-in-time accurate training data sets. The data engineer then needs to take all of that that the data scientist has built and deliver pipelines with different sets of infrastructure and different tools so they need to rewrite many feature definitions, and that's also a source of training and serving skew. They need to do online data modeling for the online store. They need to manage the orchestration, create incrementals. I'm not going to read them all, but there's a lot of work to be done by the engineering team. So this is part of what creates the long iteration times. To top it off, there's trends in feature engineering that require even more features, right? There's data freshness for online applications that are more and more requiring streaming and real-time feature processing. There's the processing of unstructured data, encoding unstructured data into a form, into a numeric vector form that's useful for signals for machine learning models. And more recently, there's the ability to generate recent context for generative AI applications. So if instead of all of this complexity, what if we had data scientists and data engineers work on a common framework, right? A common set of abstractions where they can define features and define the data processing needs of those features, and then have something that builds out all of the other elements that we talked about and automates much of the work that the teams need to do. So our point of view on approaching this is that the feature definition and implementation need to be decoupled. For this, we've created a declarative language for ML teams to use for data scientists and data engineers to work on jointly to build out these feature definitions. It needs to provide easy experimentation. So we don't want to slow down the data scientists. The whole purpose is accelerating the machine learning cycle of building models and training models. So we need the platform to allow the data scientists to continue experimenting easily while building the feature definitions using this declarative framework. And it needs to be easy to deploy to production, right? Taking those definitions and just automating the deployment to production. So you need a platform that's capable of taking those definitions and materializing them into pipelines. We need governance. So we talked about this. We need the ability to audit. So we need to store the metadata for the features, store the process data, the execution, when jobs are executing, failures, recoveries. The features themselves need to be discoverable, right? So there needs to be a repository of features so that we promote reuse and therefore provide more compute efficiency. We also believe in delivering features within this platform as data services that have the capabilities to deliver the SLAs needed for online applications. So what an ideal feature engineering workflow looks like from our perspective is that the data scientists and data engineers are able to experiment and rapidly define or reuse existing features with a shared abstraction to process real-time streaming and batch data. It needs to be easy to productionize, so to take those definitions and deploy them and automatically build the pipelines that are going to deliver those features in a continuous way. By storing the metadata, we centralize the features and control pipeline sprawl and increase reuse. And finally, with that same definition, because we have the feature vector defined that's needed for a particular model, the ability to serve should also be automated. right? We have the definition of the pipelines, the definition of the feature vector. So this platform with that definition can just deploy that serving feature vectors for both training and inference. So this is where the Tecton platform comes in, right? The Tecton platform is designed to provide that capability to process real-time streaming, batch, and unstructured data from the raw data form into the feature form and deliver them for inference with low latency and high throughput for the inferencing used by applications, for training, delivering point-in-time accurate training data sets, and delivering even context for generative AI applications. So what's this platform made of? The major components are the declarative framework. This is the language, the features as code that we're going to talk about in more detail here today. And with that declarative framework, an automated creation of the data pipelines that deliver those features in a continuous fashion. We also have specialized feature engines to deal with complex feature calculations like time window aggregations, and do so in a highly efficient way with low latency and high accuracy and high throughput. And also an embeddings engine that helps us deal with unstructured data. The enterprise feature store is where we store all the metadata, where we have the online and offline data stores, and deliver from there to the unified serving system, which is the last component, which is an auto-scalable platform that delivers an API, either through Python or through an HTTP API, to deliver feature vectors with very low latency and high throughput with the latest values. So finally, we get to features as code, right? So with this declarative framework, the idea is that within Python, within notebooks, you can define features, their sources, their transformations, in a very flexible way using Python and SQL, and then take those definitions and apply them to the platform and have the platform create these pipelines where it creates specialized and standardized materialization jobs for batch and streaming sources, feeding the offline and online stores, and finally delivering that automated serving from the online stores for model serving through an HTTP or Python API, and also delivering those real-time pipelines at serving time, and so managing that compute as well. So looking at a little more detail into what happens under the covers when you apply a set of feature definitions to the platform. First, it goes through, so going through the top row first, it goes through validation. So this checks for internal consistency and delivers and makes sure that that the data sources definitions map to the transformation definitions and the feature vectors that they're going to deliver in the end. All the data types match and all of that sort of validation. Once it passes validation, it does change detection, so it automatically deals with changes in the definitions of your features. So if this is the first time you've created features, it's going to materialize it all. If not, it just materializes or rematerializes whatever has changed that requires rematerialization. And we'll talk more about materialization when I finish the top row. But it also feeds the feature registry with all of the metadata and all of the dependencies of these features, so that you can do feature discovery and do lineage analysis and impact analysis directly in the Tecton UI. So materialization takes on multiple forms. As it decides to build these pipelines for streaming, batch, and real-time sources, it manages the compute. You select which kind of compute you want to use for either stream processing or for batch processing, or you can select from Spark structured streaming or our own managed infrastructure using the Rift engine for stream processing, or do batch processing with either Spark SQL, Snowflake, our own Rift processing with either SQL or Python, or even EMR. And so Tecton manages, deploys the pipelines, deploys the necessary compute for stream processing, monitors the stream processing engine, schedules backfill jobs, and schedules ongoing incremental jobs for batch processing as well, manages those schedules and manages the execution of those jobs and all of the resources that are needed. So it provisions the resources with the appropriate software and the appropriate packaging, even for the real-time pipelines that you build, which are completely custom code. So on the serving side, for model training, the serving engine does the time travel joins that are needed to create point in time consistent training data sets, and that's accessed through the offline API. For online retrieval, the serving engine does the retrieval, does some kind of final aggregation in some cases. We'll talk about aggregation more a bit later. It has caching capabilities to deliver the throughput and the low latency that the online API requires for model serving, and also connects directly to the real-time compute that deploys real-time data transformations with where the raw data values come in with the request. The real-time compute is used to transform those into whatever feature transformations you built and deliver the final feature vectors down to the model serving or even to enriched LLM prompts. So what are the benefits of this architecture? There's no more boilerplate code, right? You're not typically you're copying a bunch of code, either Spark code or SQL, that you then adjust and you end up with multiple versions of code. So we remove all of that because we use standardized feature pipelines that we've engineered for efficiency and speed and reliability. And based on whether you're doing streaming and what kind of compute you're using, we've pre-built these pipelines to have all those characteristics that do automatic provisioning and do the orchestration of the jobs, that do the automatic backfills and forward fills of the online and offline stores, and with a very robust and reliable retry logic. So even if you're using spot instances, for example, to lower cost, and there's a failure or the spot instance disappears, it automatically recovers from that kind of failure, while also recognizing unrecoverable errors and alerting on them. So now I'm going to delve a little deeper into the developer experience. Let me build out this slide. So at a high level, the developer experience is the data science team and the data engineering team work together with a declarative framework to define their sources, define their pipelines, and define the scheduling of batch pipelines or the scale of or the instance types. So you're allowed to define both the features, how the calculations are, and the characteristics of the pipeline. You can also use directly from a notebook, be able to train data. Generate training data by using the API, which we'll get into more detail in a bit. And finally, taking all of those definitions and applying them to the platform to get all of that automated pipeline generation and ongoing monitoring of those features in production. So what is this declarative framework, right? This at a high level, it uses let me stop here and see if we've got questions. Let me hold on a sec. I see a question. Does Tecton manage infra integrate with open table formats, Apache Iceberg, Apache Hudi, etc.? I'm going to get a little bit more into that, into what's native connections just in a second. But the short answer is yes. You can, and I'll show you how you can create custom data sources. Well, I won't show you, but I'll talk about that for Apache Iceberg or Hudi or many other sources, really anything you can access from Python. So this abstraction language is built from 4 different abstractions, right? The one is data sources, where you can define streaming, batch, and request time sources of data, of raw data. You define entities. These are the business entities that you are defining features for. So you may, have a bunch of activity-related measures that are associated to a user or to a merchant or to a product and so forth. So those are the business entities that are of interest to your own business. You create feature views. These are the transformations of the raw data to generate the features for the entities that you've defined. And finally, you have the concept of a feature service, which is the definition of essentially of a feature vector that can take features from any of the feature views that you've defined, whether they're streaming, batch, or real time, to do low latency serving and to also generate the time traveling training data that is needed for point in time correctness. So going a little deeper, the Tecton SDK is what you use within a notebook or within a Python to define data sources. We have native connections for Kafka, Kinesis. There's a push configuration that allows you to create a push endpoint to directly push events into the platform. You can define batch data sources, native connections for Snowflake, Delta Lake, S3, and Redshift. You can define real-time data sources, which is really just a definition of which parameters we expect to receive with the request, right? So it's a schema. And any custom data sources. So that's where you can connect to any of those sources that you asked about by creating what we call a source function. So a source function essentially delivers a data frame by reading from anywhere you want, from any source that you can access from Python. Let me see. I see there's a few more questions. Can I use a knowledge graph to create a common abstraction? We are thinking of including graphs. That it doesn't use graphs at this point. Does Tecton's manage? I already read that one. Okay, I think I'm up to date on the questions. Let me see the chat. Okay, we're good. So feature views. Feature views are this is an example definition of a batch feature view where you can either code in Python or SQL. You can select whether you're doing a batch, streaming, or real-time pipeline. You can define time window aggregations and embeddings, and I'll show you how those are done in a few slides. And you can select what compute to use for a particular pipeline, right? In this case, it's using Spark. One thing to note, where it says your code goes here in the on the function, so this is very flexible in terms of what you're doing inside the transformation, right? In this case, it's using the user source, so it's a user batch source that we defined above to get raw data, and it returns a transformed data frame, right? And however you transform it is, however you would transform it normally as a data scientist. And you can use SQL. There's other compute engines that we support. So part of the experience is also, reusing features. So other teams may have deployed features, or you may have deployed features in the past, so that are already have live pipelines in production, and you can access those from your notebooks by accessing a workspace, listing the feature views and their characteristics, which features they're creating, and then just acquire the feature view object to continue using in your notebook. So that promotes reuse and makes reuse easy from the Tecton SDK. When you acquire features using a feature view, so you can get data sets to test or to do training with. When you acquire them from a notebook, if it's a new feature view, it will go directly to the data source. It'll connect to whatever sources you've defined in the view, do the calculations on the fly, and deliver a data set for you to do training with or to examine. If it's already been deployed, it doesn't need to recalculate them anymore, so it just reads it directly from the offline store. So this saves quite a bit in compute. The feature services are defined within the notebook as an object you see here, a feature service, where you give it a name and you give it a list of features. In this case, it's a list of 3 different feature views, which would include all of the features in each of those feature views. You can also sub-select features from within those feature views to create the feature vector that you're ultimately going to use for serving, right? So once you deploy a feature service, you can also retrieve it if you're, like creating a retraining notebook, for example. You might just get the feature service, get a new training data set that will give you current time travel features for a set of events, which we'll look at in a second. And it also provides this high throughput, low latency serving of the current feature vector that you define. Well, for training data, the API is get features for events. So you use the feature service object and call it get features for events and provide it a list of training events, where the list of training events has a timestamp. This is where it's going to time travel to in terms of the feature values to return for that particular event. It needs to identify which entity. So, because this fraud detection model is accessing merchant and user data, it's going to need user ID and merchant ID as the entities. And it has other raw values that may come with the transaction when the event occurs, right? Like in this fraud detection example, the transaction amount would be such a value. And also, if you're doing supervised training, well, whatever label you're using for training, so that it incorporates all of those columns plus all of the features that you've defined in the feature service into a data frame that you can use directly. I talked a little bit about aggregations. Well, let me see. I think I have another question. What reporting for governance are available? I'm sorry. So the question is, what reporting for governance are available for how I document and describe the workflow, data provenance details? Yes, we provide all of the lineage. I'll show a bit of the UI when I go into the demo so you can see that part of it. And that's where you can do searching for existing features. Model card details. I'm not sure what you mean for model card details. So maybe if you can clarify that question. What exactly is the difference between online store and offline store? Okay, sorry. I will define those. So the online store is typically a key value store. It's a very fast for reading values for particular keys or for particular user ID or a merchant in that case. So it's meant for low latency, fast access to values to deliver feature vectors. Whereas an offline store is a much cheaper store. It's usually S3 with structured files, maybe Spark-K files, that stores the data for training in a more efficient way and only retrieves it for training purposes. Or Tecton actually writes to the offline store. It actually writes to both, right? It updates the offline and online stores on a continuous basis based on the definitions of your pipeline. Can I use a knowledge? Oh, I already read that one. I think I got them all right. So continuing, you can define aggregations and streaming and batch feature view. So within the feature view definition, you define which entity you're creating aggregations for. So it's going to group on that entity. So for each user, in this case, it's going to calculate the lifetime window of all of the user's transactions and a 7-day window. You can use windows anywhere from minutes to like it says here, lifetime, right? So anything within that range. A little bit about how that works and why it's efficient to use Tecton's aggregation engine. So the way it works is it either for the raw events that are coming from a stream or from a batch source, it processes them does filtering and projection and the transformations that you built into the function before aggregating. And then it does the aggregation within the Tecton engine. It uses partial aggregation to create tiles that are, if your minimum granularity is 1 minute for the time windows that you're creating, so it'll probably create 1 minute windows, but that's something that you control, the size of those tiles. And it also stores the individual events that are within the time frame that's needed to calculate those windows. At read time, it uses the pre-aggregated tiles to read less data, and with the tails and heads of the time frame, grabs the events that are necessary to complete that aggregation or those aggregations and create the final feature vector that it's delivering at inference time. There's another mode with compaction. This is for compute efficiency and for latency in larger timeframes. So sometimes, depending on the data volumes and depending on the amount of events and the length of the time frames, it's beneficial to do what's called compaction, which is taking those tiles, those 1 minute or 1 hour tiles, and maybe converting them into day or larger week, month aggregates, such that building out the longer aggregates really needs to read a lot less data from the online store in order to, at read time, in order to build those final aggregations. So we see customers using a combination of both the continuous mode and the compacted mode to deal more efficiently and to provide lower latency for model serving. We also have an embeddings engine. I put in this slide about describing what embeddings are because it was a new concept for me when I started reading about this. But it's really interesting. It takes unstructured data like text, images, or audio, and provides a numeric mapping to it, right? So it creates a multi-dimensional vector. This is showing 3D, but it could be n-dimensional. It's large dimensions to create a semantic mapping of those words or those texts, such that things that are similar are close together within that space, and things that are different are further apart. So there's many embedding models that provide different kinds of semantic mapping, and we make it really easy to include them in your code. First this slide before the code. So there's two engineering stages related to the embeddings models. There's the conversion of raw unstructured data into these feature vectors and storage of that, or at inference time also calculating them as needed for on-demand use cases, for example. And then there's the serving of it, where we've stored these embeddings ahead of time, associated them to some objects. That could be users, that could be products, whatever, and to be able to do point lookups of those features as the numeric vectors to be used in ML models, and also for different cases for like generative AIs, document search, or recommendation systems where you want to find similar things. You can use them to find a set of objects with similarity search. So building embeddings into feature pipelines with Tecton is really easy. It's just really adding one line of code. So this embedding into your feature view within the list of features, or you're just describing which column to read the unstructured data from and which model to use to calculate the embedding. And this automatically uses our embeddings engine that's been optimized to efficiently use GPU resources and other optimizations that I am not completely familiar with, that drive high efficiency and high speed of calculation of embeddings, both in batch and real-time forms. We've already talked a little bit about the flow of what happens at Tecton Applied, but it's worth repeating. A feature repository is the set of sources, entities, feature views, and services that you've defined. And when you apply it to the platform, like we said before, it validates all the object definitions. It does the diff of that code base with the priorly deployed code base. It does versioning, and it determines what the changes are and what needs to be recreated, both in the metadata, in the feature store, and as materialization, where again it orchestrates the pipelines. So it does the scheduling, it does the monitoring of those pipelines until they complete, or monitoring of streaming pipelines as they continue to operate. It provisions the resources that are needed. So it provisions the compute, the right type of compute, whether it's a Spark or our own Rift engine, or pushing down to Snowflake, for example, as when it's SQL. When it's a SQL pipeline, it does backfills to the offline store for all the history, for the training data. It models the data according to the entities that you have, and populates the online store for fast access of features. Like I said, it schedules ongoing pipelines to keep both the online and offline store up to date, and it deploys the streaming and real-time features on scalable compute and auto-scalable compute to deal with variations in the workloads. It self-monitors and has a robust retry logic, and it alerts for unrecoverable errors or when their lag increases. The enterprise feature store stores all of this metadata, so it has all of that lineage information from sources through feature views and finally to feature services. It logs the use of all of the feature services, so you can see which ones are actively being used, and allows you to retire some that are not being used anymore. So it allows you to manage all of the feature pipelines and make sure that because it promotes reusability through the search capability. It also tends to reduce the number of pipelines that are needed to produce all of these features for multiple use cases. It integrates with CI/CD pipelines. So, for example, you can set up the Tecton apply to only occur after PR reviews of the code base have occurred. It provides, like I said, searching and sharing of features, and therefore promotes that reusability. And it provides governance. It provides access control, role-based access controls, security permissions on these data flows, and it is fully SOC 2 Type 2 compliant. Part of what is included in this feature store is that integration to what you decide to be your offline and online feature stores, and it integrates with that framework or uses Tecton's own internal online feature store. So those are different deployment options that you have to use your own infrastructure or use our own. So this is where I'm going to switch over to the demo. But before I do that, let me see if there are any more questions. Okay, I think I've answered them all. Let me switch over to the demo. And walk you through what it looks like to use Tecton. So what the developer experience actually looks like. So this is a Visual Studio. It's a notebook environment with an example of building a streaming pipeline for fraud detection model. You have the boilerplate initialization where we're connecting to a particular instance of the Tecton platform. You can do this yourself. I'll give you a link to test this yourself. So this is an example where a data scientist is building a fraud detection model, right? So, as normal, they might inspect some historic data for transactions to see what the data looks like. But what we ask of the data scientists is that they use the declarative framework to access the data, to examine it, and to build out the feature transformations such that when they're done, they can deploy it and be ready for production without having any training and serving SKU related to the code, because it's the same code. So this is an example of a stream source. So you give it a name. In this case, we've used a push config. This is a way of deploying an endpoint, an HTTP endpoint, where you can push data directly into Tecton. You can also connect this to a Kafka stream or a Kinesis stream. Streaming sources also require a batch source. This is the source for backfill, so how it processes older events. Typically, or the recommended thing is that this data source, this batch data source, is actually the sink for a Kinesis or a Kafka stream. So it already contains a history of that stream that can be processed in batch for doing backfill. So anyway, you define your stream source. You can access the data directly from that stream source from any time frame you want, and it'll go and access the stream or the batch data set to produce the data and let you examine it. Then you define the entities that you're building features for. So it's really as simple as giving it a name and what identifies it. So what's going to be used as the join key when building out those point in time correct joins. And then you define the transformation. So in this stream feature view, we're the source is the transaction stream that we just defined, the entity is the user that we just defined. We're selecting compute pandas. This means that we're using Tecton's compute. In this case, I'm using the Rift engine directly on my laptop. So I pre-ran all of this because it does take some time on my laptop. But anyway, you can define the aggregations directly here. We've defined a 1-minute aggregation on the amount column, doing a sum. There's a large list of different functions that you can use. And then you define the function itself, which takes the rows from the stream and transforms them in some way. In this case, we just did a projection of the data that's coming through the stream to grab the user ID, which we need for grouping on the timestamp so that we can group on the different time windows and what we're grouping on, what we're aggregating. You could have any code you want in here that does more complex things, but this is the simplest case. Then you define a feature service, which is, like I said before, give it a name and give it the list of feature views. In this case, we're just using the streaming feature view. It could be a combination of multiple feature views. that define that data set. And we have, and then this is an example of getting training data set, right? So here I'm just building from those transactions and from a list of labeling of those transactions, labeling them as fraudulent or not. I build training events, which have the user ID, the entity that we're grouping on, have the timestamp of the transaction, have the amount that we need to aggregate on, and have the label if it's for supervised learning. And then we just call for that feature service, we call the get features for events on those training events. And this is where the magic happens. And it does all of the appropriate point in time joins that are needed to retrieve the feature values that were valid at the time of those events. And so it delivers point in time consistent feature sets with the columns from your events and all of the features that were defined with the 1 minute continuous, 1 hour, and this one's a 30-day one that we defined. You apply it to the platform. So I just pasted it here. Didn't want to make you wait through the apply process. So you can see it creates the backfill operations for the offline store and creates the online incremental processing for to keep the online store up to date. And then, to finalize the demo, this is an example of how you would reuse the features, right? So you can access the workspace, access any of the data sources that you've defined before, the feature views, and the feature services. So the rest of this is just an example of how, because we've defined a push config, we can push events and see and test the streaming capabilities and how it's going to produce those features by directly ingesting into the data source through the Python API. This can also be done through an HTTP request. And we're sending it an object, right? A user ID, a timestamp, and an amount, so a transaction. I used this to ingest some transactions this morning, and I'm not going to run through it all now, but we can use the get online features of the feature service to test that retrieval of the latest values, right? So in this example, you saw that I did 3 transactions, and if you add them up in your mind, you get the 161 value total for both the minute, the hour, and the 3rd day, because it's a new user ID, so it's the only activity that we've added for that user. I then waited for a minute and issued another transaction, and you can see there that the 1 minute continuous has that quantity. That quantity has been added to the 1 hour and to the 30-day continuous calculations, but now it's no longer seen in the 1 minute one. So anyway, that's sort of the end of the demo. Let me see if we have any more questions. I see something in the chat. Okay, that's Adriana telling you about the other events. So let me go back to the presentation and finish it out and then open it up for more questions. Oh, I went back. Hold on. So summarizing. Tecton's declarative framework abstracts and simplifies feature definition, right? You see how because it already has aggregation capability, because it already has embedding capability, and it's really flexible in terms of what code you can put in the functions that you define, whether in SQL or in Python. This declarative framework is very flexible and allows you to define the calculation of the feature. And then it automatically does the materialization of that, both for training and serving, manages all the infrastructure. It improves model performance by reducing the training serving skew. One part of that is it's generating the training data and the serving data using the same calculations. And another part is that point in time consistency that it drives when generating training data. So it really helps in removing sources of training and serving skew. And finally, provides the governance through lineage. I just remembered I forgot to show you the UI, and I'll go back to that in a second. It provides feature discovery and control, and so I'll show you a bit of that in a bit. Let me actually go back and show that before I finalize here. Let me bring up the UI. Hold on a sec. I need to build a new tab. And let's go to community tecton.ai. So you can see here an example of the UI. Actually, if the one that I had there, you can see the pipeline specifically here, where we have the transaction stream, the user transaction amount totals that it's calculating, how it's feeding the online offline store. So this provides the lineage of that particular example that we just went through. A slightly more complex example shows more feature pipelines, where we have multiple batch feature views and multiple stream feature views feeding online and offline stores, even an on-demand feature view that's transforming the data on demand, and finally serving a feature service for both generating the training data set. You can search through features here. So you can see all the feature views, examine them directly. There's filtering mechanisms, and I'm trying to remember exactly where those are. There's filters here, for example, that you can look by entity. You can look for individual feature views, by what calculation mode, by which engines are looking. So it provides searchability both for data engineers and for data scientists to find existing features and use them. I'd also, I'm not going to go into all of the permissions and stuff, but there's permission, there's monitoring capabilities of the compute and the current jobs and what's going on in the system, and what's even the feature server and what feature serving is occurring. This one's a demo, so there's not a lot going on. So anyway, back to the presentation. So many of our customers have seen the benefits that we're talking about, right? The F-150 reported, reducing their cycle time for building new models from 16 weeks to 2 weeks. Atlassian reports more accuracy in their online features. And Square saved a lot of money by using the transformation pipelines that we use, that we built, and reduced our costs significantly in creating features. Finally, I'll leave you with this link to experience it yourself, right? You can go to tecton.ai/explore and do this for yourself, right? You go through our tutorials in our Explore platform that allows you to do many of the things that I did here, and see the results directly on in the UI as you work through them. So I'll stop there and see if there's any more questions. Can you get the deck? Yes, we will deliver the deck. Model card is a structured document that provides essential details about a machine learning model. So one of the things to think about here is Tecton is not serving the models themselves, right? We integrate with model serving infrastructure, and the things that you describe, I would expect in some other infrastructure that has descriptions of those models. Tecton is really about all the feature pipelines, right? The definition of the features, the calculation of those features, the ongoing calculation, and storage of those features in online, offline store and real-time pipelines to deliver those features to the models through the serving API as feature vectors with extremely low latency. So that's where the delineation of the Tecton platform ends. So the models themselves are usually managed in other infrastructure. Hope that answers the question. What reporting or governance are available? Okay, so I showed some of that. Any other questions? Okay, good. I'll wait around a bit, see if anybody's typing a question. Let's see what's in the chat. Oh, thank you, Mike. I'm glad you liked it. I actually did it faster than I thought. I tend to talk faster when I'm on the spot. So sorry about that. All right, I'll give it another minute here to see if there's any more questions. And if not, I'll give you some time back. Thank you so much for listening to me and letting me share what I've learned with you. And so, yeah, we will be delivering the deck, and we'll be delivering the recording. I get a follow-up email with the recording if you missed any part of it and you want to listen to it again. So thank you again for coming to our webinar. And with that, I think we'll end it. Thank you.